Hi everybody, time to start chapter 31 about Faraday's law. So we're still talking about magnetic fields. This is a pretty short chapter, so we're going to try to do chapter 31 and 32 this week. So just to summarize where we are so far, in the previous two chapters we saw two different things. First, that an electric current produces a magnetic field, and second, that an external magnetic field will exert a force on an electric current or a moving electric charge. So here we're talking about two different things, the electric field that's produced by the current and an external electric field that would cause a force on an electric current or moving electric charge. So starting from that point, we're going to look at something called Faraday's law of induction. We're going to talk about something called motional EMF. So that is an electromagnetic force that is caused by motion of a couple things relative to each other. We're going to talk about Lenz's law, which is really related to Faraday's law, and induced EMF and electric fields, generators and motors and how they work, and eddy currents and where they might be desirable or not desirable. So to start out with, Faraday's experiment was to take an iron core and wrap it with a current carrying wire. And so this wire would be insulated, so we're not running current in the iron, but we are going to attach a switch to that primary coil. Then we're going to wrap a secondary coil also around that iron core and attach it to an ammeter and see what happens when we close or open the switch. So when the switch is open, obviously no current is running through the primary coil, but when we close it, we're going to see current run through that primary coil. And since current is running through that primary coil, remember, a current creates a magnetic field. So we're going to create a magnetic field in that iron donut, basically. Since we've created a magnetic field, now there's a magnetic field going through this current carrying, or this conductive secondary coil. And so when that magnetic field turns on, it goes from no magnetic field when there's no current in the primary coil to some magnetic field when there is a steady current. So there's a point where it's changing from nothing to something. And during that change, there is a current induced in that secondary coil. So that secondary coil is just hooked up to an ammeter where we can measure this, but it's not hooked up to any battery that's causing this current. So Faraday's experiment shows us that the current change in a primary coil is going to induce a current in a secondary coil. And once we reach a steady current in that primary coil, we're not going to see any induced current in the secondary coil. Okay, so Faraday's observations tell us that when you have a constant magnetic field, you're going to produce no current in a conductor. But a changing magnetic field is what's going to produce that electric current or that induced current. So a changing magnetic field induces an electromotive force or an EMF. Faraday's observations also go on to say that the more rapidly the magnetic field changes, the greater the induced EMF. And the induced EMF depends on the area of the circuit loop. So the EMF is proportional to the rate of change of magnetic flux passing through the circuit loop of area A. So what can we compare that to? Well, let's compare it to our equations with magnetic flux. So let's remind ourselves what magnetic flux is. So magnetic flux, I'm going to go ahead and underline this here. Magnetic flux, remember, is B dotted with A. So it's our magnetic field and how it goes through our current loop area. So we're going to describe an area with this current loop. So if we're going to do a dot product, we're actually going to do B times A, those magnitudes, times the cosine of theta. And now this is if B is uniform. So the cosine of theta is just the angle that our magnetic field makes with the normal of the current loop. So remember, the normal of the current loop, the normal direction, is going to be perpendicular to our current loop, right? It's going to be perpendicular to the plane described by that current loop. And actually, I'm erasing that because you use your right hand to decide which way is normal. So this I, if I wrap my fingers around in the direction of I, my normal is actually in that direction. All right, so we're going to describe our magnetic flux in that way if our magnitude of B is uniform. If it's not uniform, then we just have to do an integral over our area. So we're going to have to look at every little piece of area and the magnetic field through that piece of area and add up all those things. So that's if our magnetic field is not uniform or not at a uniform angle with our area. We're going to do an integral summation instead of just saying B dot A. So look out for those things, whether we're saying we're uniform or not. So Faraday's law of induction, we can write in this simple form. So that is our induced EMF on the left-hand side equals negative d phi dt. So d phi dt captures that the rate of change of our magnetic flux. So if it's fast, we see a bigger EMF. If it's slow, we see a smaller EMF. So it captures that observation from Faraday. It also captures the area dependence because we have area inside our equation for flux there. So the EMF induced in a circuit is equal to the rate of change of magnetic flux through the circuit. That is Faraday's law of induction. Written mathematically, it is that thing I have boxed in red. If we've got more than one loop that is current carrying, so remember Faraday's equation, he had all these loops wrapped around the iron core. So if the circuit contains n loops that are closely wrapped so that the same flux passes through each, the induced EMFs in each loop add together. So if we've got more than one loop, we're just going to have a factor of n in there. So our induced EMF, our electromotive force, motive as in we get charges to move, is negative n d phi dt. And that phi, again, is our flux that we have these equations for. Okay, so how about an example of how we would use Faraday's law of induction? So in this example, we have a coil that consists of 200 turns of wire. Each turn is a square of side 18 centimeters. Then they tell us a uniform magnetic field is directed perpendicular to the plane of the coil and it's turned on. If the field changes linearly from 0 to half a Tesla in 0.8 seconds, what is the magnitude of the induced EMF in the coil while the field is changing? So we're going to grab all these things. We've got 200 turns of wire, so we're given n equals 200 turns. We have that the turns are a square, so the area is going to be given by an equation like A equals the side squared. The side length is 18 centimeters, so I'm going to convert that to meters when I write it down in my givens, so 0.18 meters. A uniform magnetic field is directed perpendicular to the plane. So perpendicular to the plane means in the same direction or exactly the opposite direction of the normal. So either our angle is 0 or 180 degrees. It doesn't really matter which one we use. Either way, we're going to change our flux in a certain way. It says the field changes linearly. So we're given the field initially it's at 0 and finally it's at half a Tesla. So that is this information in this amount of time. So that's our delta T. And then we're going to try to find the magnitude of the induced EMF. So since we're finding magnitude, I'm going to use just the absolute value and drop any negative signs here. So when I find the magnitude, I'm going to use this general equation. So for this very specific situation, we have n turns of wire. And our flux, if we write the general equation for flux, this cosine of 0 degrees would be 1, 180 degrees would be -1, but remember we're taking an absolute value, so it doesn't really matter. We're just going to say that that cosine of theta goes to a 1, and this is delta T. Now, in this particular case, our area is not changing, so we can pull that out front. but our magnetic field is changing over time. So this is where it makes sense to think about changing linearly. We can use delta B, delta T as just a very simple, what's our final minus our initial magnetic field, and how long did that take? So I have all these numbers, right? I have n equals 200 turns. I can find A pretty quickly, right? That A is a d squared. I've got my final and my initial magnetic field and how long it took. So if I plug all of those things in and round to my sig figs, I am going to get that my induced EMF is going to be 4 volts. Easy enough, right? Okay, so that's my 4 volts. That's a good place to pause, I believe, and we'll talk about Lenz's law when I pick up on the next recording.